Welcome to Applied Math in Biotechnology, What You Need to Know. We will take a deep dive into the kinds of math questions you will see in the Applied Mathematics category of the BACE. Many of the questions you will encounter are about how to accurately make solutions of precisely defined concentration a crucial task in the biotech lab. But don't worry, we will walk through the types of calculations, what to look out for, and how to build confidence as you practice your lab math skills. We must be very comfortable with the metric system. Also known as SI units, the metric system is the numerical language of science worldwide. The units are designed for accuracy and reproducibility. In the lab, grams, liters, and moles are most often used. These units will be appended with prefixes to modify the unit by a power of 10. For example, kilo meaning 1,000 times with the symbol K, or milli meaning 1,000th with the symbol M, and micro, which is symbolized by the Greek letter mu, written like a reversed lowercase u with a long stem, meaning 1/1,000,000th. When we are talking about solutions in the lab, this is what we mean. A solution is typically a liquid mixture in which one component, the solute, is added to and dissolved into a liquid solvent. The solvent is usually water, but sometimes an organic solvent such as ethanol will be used. Solutions are a big part of biochemistry, biological and chemical-based work, as most of the reactions of life take place between molecules in aqueous solution. The SI base units you will use most often are grams for mass, liters for volume, and moles for concentration or amount. Scientific notation expresses numbers so that there is one digit to the left of the decimal point, and that number is multiplied by a power of 10. Computations are easier in scientific notation, as everything is expressed in relation to a power of 10, and some very large numbers are easier to write. For example, instead of writing 602.214.000.000.000.000.000, when we are talking about the number of atoms in a mole, we can just write 6.02 times 10 to the 23rd. The metric system and scientific notation go hand in hand, making unit conversion straightforward. They help you set up equations so that the units will cancel when you multiply through. Solution concentrations are often expressed as some quantity of mass per unit volume. You will run into these often in the lab when working with purified protein or amplified DNA samples, or when preparing cell culture media. These solutions are described by the formula concentration equals mass divided by volume. Mass over volume concentrations can be written as mg per mil, or milligrams per milliliter, grams per liter, micrograms per microliter, and even nanograms per milliliter for very dilute solutions. Convert units if necessary, so you can cancel them out correctly during your calculation. You should be able to easily convert, for example, 250 milliliters to 0.25 liters, or 50 microliters to 0.05 mils. Remember, we can arrange the formula to solve for mass. Concentration times volume equals mass. Here is an example. How many milligrams of the antibiotic kanamycin are needed to make 11.5 mils of a 50 mg per mil stock solution? Let's inventory what we know. Our desired concentration is 50 mg per mil. The volume we want to make is 11.5 milliliters. And we're being asked for the mass in milligrams, so we know how much kanamycin to weigh out. We set up our equation as follows: concentration desired times volume desired, and solve for the amount of kanamycin powder, our solute. No conversions needed here. Cancel out the milliliters and the units match. 575 milligrams. Sometimes the solution we want to prepare is described as a percent solution, that is, the parts of solute in 100 parts solvent. With percent solutions, we see two main types. For percent mass, or weight per volume, 1% W/V equals 1 gram per 100 mils, and for percent volume per unit volume, 1% V/V equals 1 mil in a total volume of 100 milliliters. As an aside, recall that mass is a property of matter, while weight is the force that gravity imposes on that matter. On Earth, mass equals weight. We can convert the percentage concentration into a decimal value by moving the decimal point to the left. 12% becomes 0.12, 75% 0.75, and 40% equals 0.4. The units will be in grams and milliliters. We use the familiar formula, concentration as a decimal value times volume equals the mass. Let us work a percent mass volume problem. What is the mass in grams required to make 150 milliliters of a 60% weight/volume solution of ammonium sulfate? Record our inventory of variables. For a final concentration of 60%, we write it as 0.6. The volume is 150 milliliters, and we wish to solve for the weight or mass of the salt in grams. We use the same equation, plug in our values, and voila! We will need 90 grams of our solute. Similarly, we can work out a percent volume/volume problem. What is the volume in milliliters required to make 750 milliliters, or 0.75 liters, of a 70% volume/volume solution of ethanol in water? Do not be confused by the 100% here. It means we are using a pure liquid solute, in this case 100% ethanol. To prepare a final concentration of 70%, we write it as 0.70. The volume desired is 750 milliliters, and we wish to solve for the volume of solute. Convert percent to decimal and liters to milliliters, plug in our values, and we find we need 525 milliliters of our solute. Molarity is another way to describe the concentration of a solution. Molar concentration, or molarity, is just the number of moles of solute per liter of solution. What is a mole? A mole is exactly 6.022 times 10 to the 23 elementary particles, such as atoms, molecules, or ions. This is known as Avogadro's number, and it is very useful in chemistry when we want to compare amounts of atoms or molecules. We can simply think of a mole as a term to define a quantity of a substance, like a dozen eggs or a byte of data. With molar solutions, we are expressing the concentration of solute in moles per liter, and the symbol is capital M for molar, or little m big M for millimolar. Molarity is the most frequently used method to express concentration in a biochemistry lab. It can be used to precisely describe highly dilute solutions or very small amounts. We use the molecular weight or formula weight of a solute to calculate molar concentration, and these are reported as grams per mole. Every chemical species, whether that is an element, a molecule, an ion, or even a compound like a salt, with different hydration states, every chemical species has a molar mass, also known as the molecular weight, abbreviated MW, based on the combined atomic weights of the atoms in it. The units for molecular weight are grams per mole and will be provided when you are asked to work with molar concentrations. This number can be found on the label or calculated from the periodic table and can also be reported as formula weight because some chemicals come as hydrates, meaning that those compounds contain chemically bound water. Molar concentration is the number of moles of solute per liter of solution, abbreviated with a capital M. As an example, sodium chloride, NaCl, has 1 atom of sodium and 1 atom of chlorine. The formula or molecular weight of sodium chloride is 58.44 grams per mole. How do we know this? On the periodic table, we can see that the atomic weight of sodium is 22.99 grams per mole, and chlorine is 35.45 grams per mole. Right, so the molar mass of sodium chloride is 58.44 grams per mole. The equation to use here is concentration desired in moles per liter times volume desired times molecular weight in grams per mole, giving us the mass of solute in grams as the moles and volume units cancel out. Let us use the molar mass or molecular weight of potassium chloride to prepare a 3-molar solution. We are given the desired concentration, 3 molar, and the volume desired, 100 mL, and the molecular weight, 74.555 grams per mole. When we plug these variables into our equation, being careful to make sure the units match by expressing 100 mL as 0.1 liters, the units drop out, giving us the answer in grams. Remember to use the correct number of decimal places in your answer. Next, let us talk about calculations involving dilutions. In the lab, we often find it convenient to prepare concentrated stock solutions. These can save us time and storage space on the bench. It is convenient to prepare a working solution by diluting a prepared stock. And this is where we encounter the most commonly used equation in every bioscience lab. C1 times V1 equals C2 times V2. This simply represents the proportional relationship between a concentrated stock and the final diluted solution concentration. Initial concentration, or C1, times the initial volume, V1, equals the final concentration, C2, multiplied by the final volume desired, V2. Normally, we are solving for V1, so we can rewrite the equation as V1 equals C2 times V2 divided by C1. Let us say we want to make LB media with 100 micrograms per ml of ampicillin. We have a stock solution at a concentration of 50 mg per ml. How much of the stock do we need to add to prepare 600 ml of LB plus amp? Record our variables. C1 is our 50 mg per ml stock concentration. V1 is our unknown. C2 is the desired concentration in micrograms per ml, which we convert to milligrams per ml. And finally, the desired volume is 600 ml. Plugging in our variables to the C1 times V1 equals C2 times V2 equation and moving it around to solve for V1, we get our answer, 1.2 ml of the concentrated ampicillin stock. A serial dilution is a series of dilutions, with the dilution factor staying the same for each step. The concentration factor is the initial volume divided by the final solution volume. The dilution factor is the inverse of the concentration factor. For example, If you take 1 part of a sample and add 9 parts of water, or solvent, then you have made a 1 in 10 dilution, and this has a concentration of 1/10 of the original and a dilution factor of 10. These dilutions are often used to create a range of standards of known concentration to be quantified in an assay, which we can use to compare with an unknown sample to arrive at an approximate concentration and thus quantify our unknown. Serial dilutions allow for small aliquots to be diluted, are cost-effective, and are easy to prepare. This is often used when creating standard curves. Let us say you start with a 4.0 mg per ml protein solution and need to make a 5-step, 2-fold serial dilution. What is the concentration after the last step? This is a 2-fold dilution, so we will divide by 2 5 times. So 2 to the power of 5, or 2 times 2 times 2 times 2, which equals 32. 4.0 divided by 32 equals 0.125 milligram per milliliter. But the question says round to 2 decimal places. Our final answer, 0.13 mg per ml. If you enter 0.125, it is incorrect. Pay attention to those rounding instructions. Now that you've seen the types of problems, here are some tips to build your confidence. Practice all year. Don't wait until test prep season. If you can do a little applied math every week in warm-ups, lab prep, or homework, it becomes easier and less intimidating. Expect to see it everywhere. Some teachers include an applied math question on every unit test. If you know it's coming, you'll be ready. Prep your own lab materials. If your teacher gives you the chance, try doing the calculations for the labs yourself, not just following the directions. It'll help you connect the math to the real work of a biotech technician. Talk to your other teachers. Chemistry and math teachers can help you see these concepts from different angles. If something's confusing, ask how they teach it. That crossover can really help. Applied math may seem tough at first, but it's one of the most valuable tools you can bring into a biotech career. Focus on the units, watch for rounding, get in the habit of breaking down each problem and writing down all the known quantities and units. The BACE Practice Exam course is your guide to mastering the Biotechnology Aptitude and Competency exam. The more you practice your biotech math skills, the more confident and accurate you'll become. Good luck on your journey to mastering the BACE.